a background in network QoS, it can be a little daunting, so I thought I would take some time to walk you through a layer 2, layer 3 uplink and downlink message exchange between a client and a server. First, let's talk about how end-to-end QoS happens with a controller with thin APs. In order to do this, let's take the process step by step from the client device, in this case a phone, to the server, in this case an IP-PBX. In step 1, a WMM-capable client device's application marks its outgoing messages with user priority or UP bits, which, as they go down the client's OSI stack, get mapped to DSCP bits in the IP header and WMM/802.11e UP fields in the 802.11 frame header. The UP information is also used to put the 802.11 frames into the correct outgoing WMM access categories, sometimes you'll see them referred to as ACs, on the client devices for prioritized transmission. Now that the layer 2 and layer 3 markings are in place, the frame is transmitted when its WMM AC wins access to the wireless medium. In step 2, the thin AP receives the frame. Thin APs do not support Ethernet frame header expansion, and so they use access connections. Additionally, thin APs form tunnels using various proprietary and standardized tunneling protocols to connect over the Ethernet infrastructure to the controller. Most of these tunnels wrap the entire 802.11 frame inside of a tunnel wrapper, which is then placed inside of a layer 3 packet. Depending on the size of the 802.11 frame, it may actually require 2 packets to get the 802.11 frame to the controller. The layer 3 packet is then placed inside of an Ethernet frame and shipped off to the controller. With this process, you now have inner and outer layer 2 frames and layer 3 packets to deal with for QoS. The original IP packet is marked with DSCP, and the original 802.11 frame is marked with UP bits in its header. At the access point, the 802.11 frame is placed into another IP packet that is now marked with DSCP markings of its own, which are based on the original 802.11e UP markings. The 1 or 2 IP packets that are created to carry the 802.11 frame to the controller are now placed into Ethernet frames, which have no QoS markings because they don't have the expanded frame header. In step 3, when the layer 2 edge switch receives the Ethernet frame, it does not understand the DSCP markings, and the Ethernet frame header has no 802.1p bits. This means that no prioritization happens at the layer 2 switch, which can easily lead to congestion and latency. The layer 2 switch has a trunk connection to its upstream layer 3 distribution or core Ethernet switch. This means that the Ethernet frames sent over the link have 802.1p Ethernet header fields, but they go unused since there's nothing to indicate to the layer 2 switch what to put into those fields. Remember, it does not understand the IP headers and has no 802.1p markings to go on for the incoming Ethernet frame. When the layer 3 switch receives the frame, it removes the IP packet from the Ethernet frame, reads the IP packet's DSCP value, and prioritize the packet appropriately for egress. In step 4, upon exit, the packet is placed into a new Ethernet frame that is marked with 802.1p in its header and shipped to the controller. The value used for the 802.1p marking is based on the DSCP marking in the IP header. Keep in mind that this is a layer 3 switch which understands both the layer 2 and the layer 3 markings. A QoS marking map must be configured in the layer 3 switch in order to properly map the DSCP to 802.1p bits. And the layer 3 switch must be configured to trust the incoming values at the downlink port. The WLAN controller, in step 5, receives the Ethernet frame. The 802.1p markings are read and honored, the IP packet is removed from the Ethernet frame, and the outer IP packet headers DSCP markings are also read and honored. Hopefully, the DSCP and 802.1p markings indicate the same priority to the controller. The controller removes the IP header, the tunnel wrapper, and is now left with only the original 802.11 MAC frame, which has 802.11e UP markings in its header. Those values are read and honored, and the 802.11 header is removed, and only the original IP packet now remains. The controller reads the IP headers, DSCP markings, in order to now prioritize and possibly remark upon egress if needed the processing of this payload. The IP payload is now placed into an Ethernet frame, which is marked with 802.1p based on a mapping to DSCP, and it's shipped back to the layer 3 switch. We call this a traffic U-turn, and it causes latency and a single point of failure in the network. When the layer 3 switch receives the Ethernet frame in step 6, it reads the 802.1p bits, prioritizes the frame appropriately, and finds out which port the destination station is connected to. If the destination port is an access port, there will be no frame header expansion, but the DSCP values will remain in the IP header. If the server supports a trunk connection, 802.1p prioritization at layer 2 can also be used. When the server receives the frame, it will remove the IP packet from the Ethernet frame, read the DSCP value in the IP header, and will prioritize the message appropriately. Did you get all of that? I sure hope so, because now we're going to do it in reverse to see if we can spot some additional issues. As a quick recap, the issues with uplink QoS in a controller-based Wi-Fi infrastructure are that the layer 2 edge switch doesn't prioritize traffic because it can't read the DSCP markings, doesn't mark the Ethernet frame destined to the layer 3 switch, and the controller introduces a bottleneck, significant latency, and a single point of failure. Would you like to see that in reverse? Here goes. In step 1, the server sends an IP packet marked with DSCP to the layer 3 switch, but before it goes out, it's placed in an Ethernet frame that is typically not marked with 802.1p because the server is connected to the layer 3 switch with an access connection. In step 2, the layer 3 switch receives the Ethernet frame, removes the IP packet, reads the DSCP value in the IP header, and prioritizes the traffic for egress appropriately. The link to the controller is a trunk connection, so both layer 2 and layer 3 are marked. The Ethernet frame goes into the controller, and tunnel packets encapsulated in Ethernet frames come back out. We're back to that IP packet inside of an 802.11 frame, inside of a tunnel wrapper, inside of another IP packet, inside of an Ethernet frame scenario. All frames and packets should be marked with appropriate DSCP and 802.1p markings at this point. Depending on the size of the downlink 802.11 frame, this might actually be 2 tunneled IP packets going out. Note that it takes time and horsepower to convert something as simple as an IP packet to these overbloated carrier pigeons destined to the thin AP. That time translates into unnecessary and often excessive application layer latency. After the step 3 traffic U-turn, the layer 3 switch receives the downlink Ethernet frames, reads the 802.1p and DSCP markings, prioritizes appropriately, and then ships the new Ethernet frame off to the layer 2 edge switch through a trunk connection as shown in step 4. When the layer 2 switch receives the downlink Ethernet frame in step 5, it can prioritize it appropriately due to the 802.1p marking. It removes the frame header expansion and places the Ethernet frame on the egress link to the AP, still marked with DSCP, and the AP then receives it. The AP removes the Ethernet frame, reads the DSCP marking, removes the IP header, the tunnel wrapper, and is then left with a priority value and an 802.11 frame. In step 5, the 802.11 frame is marked with the appropriate UP according to the value found in the IP packet's header DSCP value, and put into the appropriate access category for transmission onto the wireless medium. The client receives the 802.11 frame, reads the header's UP value, removes the frame, reads the DSCP value in the IP packet header, removes the payload from the IP frame, and then sends the message up the OSI stack to the application. Piece of cake, right? Except for the traffic U-turns latency and the fact that the controller can be a tremendous traffic bottleneck, downlink QoS should work fairly well in a controller-based scenario under light loads. When moving from a fast switched network like gigabit Ethernet to a much slower shared medium like 802.11, good QoS is not just a nice-to-have feature. It's absolutely essential. Think of it like moving from a 4-lane highway to a 2-lane highway. When it's not busy, it's not a big deal. But when it's crowded and a voice frame ambulance needs to get through, it's life or death for your applications. Prioritizing downlink traffic at the controller rather than at the AP is like trying to prioritize cars, trucks, and ambulances miles ahead of where they will have to be put into the proper order on the highway. Looking at the graphic, would you prioritize traffic at the red X or at the green checkbox? I think that's called a rhetorical question. Thanks for attending Aerohive's QoS presentation. Please visit aerohive.com/register to check out our free Wi-Fi network planning tool and Hive Manager online, and have a great day.